Problem 83. Use calculus techniques to sketch a graph of the function x over x squared minus 1. We're going to break this problem into three phases. The first involves the information we can extract just from the original function, and this includes asymptotes and intercepts. So we're going to look at the x-intercept, the y-intercept, the horizontal asymptote, vertical asymptote. So let's look at each of these one by one. So first, to get the x-intercept, we set y equal to 0. So in this equation, we've got 0 equals x over x squared minus 1. Multiplying both sides by x squared minus 1, we get 0 equals x. Now here we had set y equal to 0, and we had gotten x equals 0. So our x-intercept is 0, 0. Let's update that in our table. 0, 0 for the x-intercept. Now for the y-intercept, we work accordingly. To get the y-intercept, you set x equal to 0. So this gives us y equals 0 over 0 squared minus 1. And this gives us y equals 0. So we had set x equal to 0 and got y equals 0. So let's update the y-intercept in our table. This 0, 0. Not any new information, but it's important to go through the method anyway. The next part of the problem, we're looking at asymptotes. So to find the horizontal asymptotes, we take the limit as x goes to 0 on the original function, and the limit as x goes to negative infinity on the original function. This first problem we can solve by dividing both the numerator and denominator by x squared. I do that because that's the highest power of x I see in the denominator. This gives us a limit as x goes to infinity of 1 over x divided by 1 minus 1 over x squared. In the numerator, 1 over infinity goes to 0. In the denominator, this is still 1, it has no x's in it. 1 over x squared also goes to 0. 0 divided by 1 gives us 0. So our first horizontal asymptote is y equals 0. Let's go plug that in the table also. Now our next horizontal asymptote, we can evaluate this limit the same way. We can divide both the numerator and denominator by x squared. This gives us the same limit we had before, but now as x goes to negative infinity. 1 over x, 1 minus 1 over x squared. And just like before, we have 0 in the numerator, and then 1 minus 0 in the denominator, and this gives us the same limit. So the horizontal asymptote to the right and the horizontal asymptote on the left are actually the same. They're both y equals 0. Now let's look at the vertical asymptote. To get our vertical asymptote, we look to see where the denominator of our function is 0. So set x squared minus 1 equal to 0. We can factor this up as x plus 1 times x minus 1 equals 0. Splitting this into two equations, we get x equals negative 1 and x equals positive 1 for our vertical asymptotes. So we add these to the summary. X equals 1, x equals negative 1 for our vertical asymptotes. Now we've done everything we can based on the original function. We're going to move on to its derivative. So for the derivative, we're going to look at maximums and minimums, as well as intervals of increase and decrease. So let's move on to the derivative. Given the original function is x over x squared minus 1, we can differentiate using the product rule and simplify, and we should get this as our derivative. So to get the critical numbers, we want to see where is the derivative 0 and where is it undefined. So we'll set 0 equal to our function, and we'll see where this is undefined, which is where the denominator is 0. So if the function is 0, that amounts to setting its numerator equal to 0, so x squared plus 1 equals 0. And this gives us no solutions. So we get no critical points from the derivative being equal to 0. To see where it's undefined, we're going to take the square root of both sides. So we get x squared minus 1 equals 0. We can factor this up and we get x equals 1, x equals negative 1. Now these are not critical numbers, because the original function itself is undefined at these points. These are actually vertical asymptotes. But they are important to note to find intervals of increase and decrease. So what we'll do is we're set up our interval. We know the only points that really matter on this are x equals 1 and x equals -1. So we'll pick test values on either side of this interval. Say x equals -2, x equals 0, and x equals +2. And we'll plug each of these x values into the derivative. So plugging -2 into our derivative, we get y prime equals -5/9. Plugging x equals 0 into our derivative, we get y prime is -1. Plugging x equals +2 into our derivative, we get -5/9. Now this -5/9 says that in the first interval the function is decreasing because its derivative is negative. The function is decreasing here because the derivative is negative. And the function is decreasing here, so our derivative is negative. So we see it's decreasing in every one of these intervals. So we see that we have, in particular, no maxes or mins because the function is decreasing on every interval. So going back to the table of values, we have no maximum, we have no minimum, the function is never increasing, it decreases from -∞ to -1, it decreases again from -1 to +1, and it decreases again from +1 to +∞. So we've got all the information we can get from the first derivative. Now we go on to the second derivative. The second derivative involves points of inflection and intervals where the function is concave up and where it's concave down. So now let's move on to the second derivative. Taking the derivative of g prime and simplifying, we get this as its second derivative. So what we'll do is we want to see where this is 0 and where it's undefined. So if we set g prime of x equal to 0, we get 0 equals 2x times x squared plus 3 over x squared minus 1 cubed. And to see where it's undefined, we set the denominator equal to 0. So x squared minus 1 cubed equals 0. For this first equation, we multiply both sides by the denominator to get 0 equals 2x times x squared plus 3. Splitting this into two equations, we get x equals 0 from our first factor. And the second factor is never equal to 0. It's never negative because we have x squared plus 3, a square plus a positive. This is never negative, never 0. So we have as our only possible point of inflection from where the second derivative is 0 happens at x equals 0. To see where it's undefined, on the second equation we can take the cube root of both sides. We get 0 equals x squared minus 1. We can factor this into x plus 1 times x minus 1 equals 0. Splitting this into two separate equations, we get x equals -1, x equals +1. Again, those are the vertical asymptotes on our original function. So we'll do another interval test. We now have x equals -1, x equals 0, and x equals +1 as our critical numbers. Now we pick test values as we did before. In this interval, I'll choose x equals -2. And here, maybe x equals -1/2. In this third interval, x equals +1/2. And over here to the right, x equals +2. Now plugging each of these into the second derivative, in this first interval, I have that the second derivative is -28 over 27. At x equals -1/2, the second derivative is +208 over 27. On this third interval, we plug in x equals +1/2. We get that y double prime is -208 over 27. And in the last interval, we get y double prime is +28 over 27. Since the second derivative is negative on this first interval, we know the function's concave down. It's positive in the second interval, so we know the function is concave up. Between 0 and 1, the second derivative was negative, so we know the function's concave down. And to the right, the second derivative is positive, so we know the function is concave up. So updating these back on our original table, we know that the function was concave up from -1 to 0, and again from 1 to infinity. We know that the function was concave down from -∞ to -1, and again from 0 to 1. Now our only point of inflection in here, it looks like it changed concavity at x equals -1, but that was a vertical asymptote. It changed concavity again at x equals 0, so that actually is a point of inflection at 0, 0. At x equals 1, it changed concavity again, but that was a vertical asymptote. So we have enough information for a graph. Let's sketch this out and see what it looks like. Using the information from the original function, we have our only intercept at 0, 0. We have a horizontal asymptote at y equals 0. We have a vertical asymptote at x equals 1 and at x equals negative 1. So that summarizes the information we have from the original function. From the derivative, we know that the function is decreasing from negative infinity to negative 1. So it comes in from this asymptote and it decreases to x equals negative 1. It's decreasing again from negative 1 to positive 1. So it decreases from this vertical asymptote, passes through the intercept, and then continues to decrease down toward the second asymptote. And it's decreasing again from 1 to infinity. So at x equals 1, it comes in on this vertical asymptote and continues to decrease until it approaches that horizontal asymptote to the right. And now we move on to the second derivative information. The function is concave down from negative infinity to negative 1. Concave down throughout here. That verifies that what we've done so far is correct. It's concave up from negative 1 to 0. So from negative 1 to x equals 0, it's concave up. That makes sense from what we have here. We have this point of inflection at 0, 0. And then it becomes concave down from 0 to 1. So concave down from x equals 0 to x equals 1. That again makes sense from our graph. And then finally, it's concave up from 1 to infinity. So from x equals 1 out to x equals infinity, it's concave up. So the graph that we have here seems consistent with the information from the original function, from the first derivative, and from the second derivative.